Greetings, we are the Royal Engineers from the University of Scranton. Our advisor is Professor Nicholas Trunkel, and we are here today to present to you our embedded system, the Universal Motor Controller. My name is Nathan Williams. I am a junior electrical engineering major, and I am the team leader for this project.
Hi, I'm Luke Alonzo. I'm a freshman in electrical engineering, and I did hardware and software development.
Hi, my name is Timothy Thomas. I'm an electrical engineer junior, and I worked with hardware.
Hi, my name is Benjamin Degler. I'm a senior software developer, and I worked on the app side.
We hope you enjoy our presentation.
As engineers, it is our job to use many different types of motors, as you can see in my hands. The problem is building circuits every single time you have to use a motor. What if there was a way that you could universally control these motors? Well, the solution is the Universal Motor Controller. It's a self-contained, open-source, cost-effective device that has the ability to universally control all the different types of motors.
Now we're going to be talking about the main presentation topics. First is defining the challenge. Then we will be talking about the key functionality of the Universal Motor Controller. The next step is evaluating the performance of the main use cases, followed by the technical ingenuity of the device. One of the last steps is the project execution, and then finally is recommendations and the next steps.
The motivation behind this project stemmed from the extensive use of motor-operated devices in a multitude of projects at the University of Scranton. We realized that we were spending a lot of time interfacing the same set of components and circuits in the same way to control the same type of motors. We created a self-contained, cost-effective, and open-source device in order to reduce the time we were losing over repeating the same processes over and over again. The three examples of the device's requirements are interfacing multiple types of motors simultaneously, providing each motor with appropriate power requirements, and finally controlling motors through a mobile application. In order to test the Universal Motor Controller, we wanted to apply it to various projects that have already existed at the University of Scranton. The first being a single-axis solar tracking device developed in the Department of Physics and Engineering, the second being a two-axis telescope for our astronomy club, and finally, a three-axis laser pointing device, pictured to the right, that was printed using our department's printer. We've never controlled multiple types of motors simultaneously before, and this is one feature that the telescope required because celestial objects move relative to the observer. So we would have to take into consideration how far the object moved while one of the motors was moving the telescope. So one performance measure that we implemented was to see if we actually were tracking a specified celestial object during the movement of the device. In order to ensure that we were, we plan on integrating a camera into the system to have visual confirmation of the current position of the telescope in relation to the celestial object.
What is the Universal Motor Controller? It is a device containing four main subsystems. When integrated, the system can control multiple types of motors via an Android mobile application. What can it do? The device allows the user to plug in three different types of motors: direct current DC motors, stepper motors, and servo control motors. The user can then interact with the mobile application, either choosing a predefined sequence or create a user-defined sequence to control the motor. The four main subsystems include a voltage regulation network, motor driving circuits, an Android application, and the Intel Edison embedded controller.
Here is the voltage regulation network subsystem. Each motor that the Universal Motor Controller powers gets one of these. We power the Universal Motor Controller with a 12-volt, 4-amp power supply that is the input to the voltage regulation network. We are able to provide 5 to 12 volts across our load depending on the size of a pulse width modulation duty cycle, sent into our voltage regulating chip from the Intel Edison. In the diagram shown here, the 741 op-amp is used to buffer the pulse width modulation signal to clean up any noise. The takeaway from this is that the network provides correct power requirements for interface motors. The first type of motor we can control is a DC motor. One can control a DC motor by using an H-bridge, which is just 4 transistors acting as electronic switches. We can supply the H-bridge with power for a motor, and depending on which digital outputs from the Edison you set high, the switches can change the direction of the current which flows from your DC motor, thus allowing for bidirectional control of a DC motor. The second type of motor we can control is the stepper motor. With the use of a step-stick stepper control chip, there are 2 GPIO pins from the Edison which control the number of steps from the stepper motor and in what direction to move the axle. On the screen you can see that GPIO 4 and GPIO 5 control the step and direction. The other 4 control GPIO pins are used to enable the stepper motor and to set the amount of degrees per step. The takeaway from this is that with the UMC, we have the ability to control the number of steps and the direction of the stepper motor. The third and final type of motor we can control is the servo-controlled motor. With use of the servo control chip breakout board, we can connect it to the I2C ports of the Edison. It is used for attaching lower speed peripherals to processors in embedded systems. The motor controller is designed to power and control 3 servo motors based upon power requirements of the other motors, but this chip is capable of connecting up to 16 servo motors. Like all the servo-controlled motors, this chip accepts a pulse-modulated signal to rotate a specific amount of degrees or angle. Now that we've talked about the subsystems, this is how they will be integrated. The voltage regulation network, the motor controlling circuits, and the Intel Edison are integrated with controls from the Android mobile application. The user inputs data into the mobile application, which then sends that data via Bluetooth to the Intel Edison. The Edison then processes the data and gives commands to the voltage regulation network in the form of a PWM signal and kicks off Python control scripts, which operate the motor controlling circuits. When the voltage regulation network and the motor controlling circuits are active, the motors connected to the UMC become operational. This is the first example of our motor application. You will be watching a short clip of our single-axis solar tracking device finding the sun.
Tracking the sun. Alright, so first it's just going to move to the sun's position.
This is the second example of our motor application. You'll be watching a short clip on the 2-axis telescope.
In action, and right now it's moving in the azimuth to the current position of the planet Jupiter. So we're going to see it go and stop at 189 degrees from home, and now it's going to go up to the position of Jupiter. So we have it set so that it will stop and then track every 15 seconds. So it should be stopping right around now. Perfect.
And now this is our final motor application, the 3-axis laser pointing device.
I'm showing you the 3-axis pointing device, which is the gimbal. We have a laser pointer pointing at home position, which is going to show that we can use roll, pitch, and yaw and make it go from 3D to a 2D space, which is going to be the floor. We have some targets set up to hit it, so I'm going to run the program now. The first target we're going to do is the stepper motor with some sunglasses on it. So it's going from home position here, and it just maps out where it's supposed to go. There we go, we hit the stepper motor with sunglasses right on the peak of where the nose would be on the sunglasses, just to add the effect. Next, I think we're going to go to Barbie with a Minecraft sword. This is showing the pitch and yaw.
We have now shown our ability to control each type of motor. The next step was developing the app.
Okay, so now we're going to demonstrate how the application actually works. So what we're first going to do is we're going to connect to the Intel Edison server. So we click on Connect to Device. As you can see, it already says that we've been paired with BlueZ, which is the name of the server. But what we're going to do right now, just to show you for demonstration, is we're going to scan for devices. So what this is doing is it's pinging for other Bluetooth devices within the proximity of the tablet that we're using. And when it finds them, it presents just some basic information to us so we know who they are and if we should connect to them or not. In our case, though, we don't want to connect to any of the other devices, and we want to connect to the one that's named BlueZ with a MAC address of 004334B1BEEF. So now that the scanning is finished, we go ahead and click on BlueZ. And that's going to give us some general information about the device below, tell us that it's connected, and then we're ready to interact with the device. So what we're first going to do is we're going to demonstrate how to configure a few ports, and then we're going to select a sequence to run. So first we're going to click on Configure Motors and Sensors. And you can see we have 3 types of motors, a stepper, a servo, and a DC. For the purpose of the moon tracker, we're going to configure 2 of the stepper motors. So we click on Stepper 1, and as you can see, we can enter in a voltage and then a step. So we're going to enter in a voltage of, say, 0.5 volts, and then we're going to enter a step of, say, 0.25. Now, what we're going to do is when we click transmit data, a generic data package is made that is going to be sent to the Intel Edison server to then configure the specific stepper that we just transmitted the data for. So what we do now is click on transmit data, and for the purpose of testing, it just prints out the data that we're going to be sending, and then it go ahead and it sends that data to the Intel Edison server. Now, what we want to do is we want to configure stepper 2. So what we're going to do is click on stepper 2. Now we have the option of entering a voltage and step for this stepper. So we go ahead and enter in a volts of, say, 4.2 with a step of 0.25 as well. So again, we're going to click on transmit data. It's going to create that generic data package, and then it's going to send it off to the server to save those configurations that we've done for the motors. So we click on transmit data. Again, it displays the data there at the bottom just for the purpose of testing right now, and the port is going to be configured on the Intel Edison. So now what we want to do is, since we've completed configuring this motor, we can go ahead and click on stepper 2 configuring to close the window on the right-hand side, although that is unnecessary. And then you can click the button and it brings us back to the main page. So now what we're going to do is we're going to configure a sequence. So you go ahead and we click on select sequence, and you can see we have the moon tracker, the reflective sun tracker, and laser pointer tracker. For this purpose of the demonstration, we're going to do the moon tracker. So we go ahead and click on moon tracker, and it brings up a longitude, a latitude, and a date time. Now you have the option of entering in the information on your own if you know it, but if not, we have included an autofill button for you just to be a little bit more convenient. So when you click that button, it goes ahead and fills in the longitude and latitude and date time with the current longitude, latitude, and date time. Based off of your current Wi-Fi connection, it'll determine all that information for you. So then we're going to go ahead and click transmit data. Now this is a little bit different than configuring a motor that you saw in the previous step. But we're going to go ahead and click on transmit data, and what happens is that data is put into the generic package, sent to the Android application main activity, and then that activity information for the specific sequence is sent back to the main screen fragment. So now we have the option of starting and stopping the sequence. So we're going to go ahead and click on start sequence, and then what that is going to do is it's going to send the information from that generic data package to the Intel Edison server, and then once the server receives that, there are a few methods that are going to be run pertaining to the specific moon tracker sequence, where it's going to go ahead, determine the position of the moon relative to your current location, and start tracking it for you with the telescope. So we go ahead and click on start sequence. It'll tell you that it sent the data package to the Intel Edison, and then once all that is completed, you can go ahead and click stop sequence, and the moon tracker will stop wherever it is during its implementation of the sequence. So you can go ahead and maybe configure the motor differently, or if you want to change your current latitude and longitude, you can go ahead and do that as well.
The functionality is made possible through the use of the Intel Edison embedded controller, which has, for example, general-purpose input-output pins, I2C communication, and many other necessary components to fulfill the requirements of our universal motor controller. Our universal motor controller successfully controls multiple types of motors at the same time, supplies the power requirements for each motor, and is controlled by a mobile application. Since we are using current technology that already exists, we are simply repurposing existing components to serve a new and unique purpose.
Now for our execution overview, I'm going to briefly discuss some of the significant challenges we encountered. We had to test to make sure that we could power 9 different motors with the use of multiple pulse modulation voltage regulation. This led to the challenge we initially ran into, which is the range of voltages we are able to get from the voltage regulation chip. Another challenge was the low frequency pulse width modulation. We had to test to make sure that the simulated out DC voltage would work with the actual components that require a real DC signal. Another challenge faced was when the data was sent from the app to the Python server on the Edison, we didn't know how to decipher the data we were seeing. The solutions to these challenges are that first we had to find the right combination of resistor and capacitor values to give us the correct range of 5 to 12 volts we were looking for. Then testing was done with a low frequency pulse width modulation, and the simulated DC voltage worked like a real DC signal as expected. Finally, for the problem with deciphering the data we were seeing, it was found that the first byte was the header byte, which told the server what type it was, and then the following array of bytes was the information. So the solution was easy, to write a function to identify the header byte and then store the actual information. To talk about risk management a little bit, we made a decision based upon time to not implement the camera tracking system, since it was not essential for the universal motor controller. And then finally, to talk about budget, funds that were requested for the purchase of materials and supplies necessary to develop this universal motor controller included an Android tablet for interfacing, testing, and data collection of the device, which is around $400. There was also an Intel Atom device, which was required for the device, which was $100. And additional funds included printed circuit boards for the implementation of developed device, primary components, and miscellaneous hardware essential to its operation. In total, it was around $1,400. On to the final portion of our presentation, recommendations and next steps. Where do we go from here?
The next steps for future development of the universal motor controller involve creating a more friendly user interface between the mobile application and the Intel Edison, and to also increase the overall efficiency of the voltage regulation circuit and to reduce the overall cost of the motor controller. To do this, we plan on employing an integrated development environment onto the mobile application, which then uploads the scripts to the Intel Edison rather than the Edison hosting a server which deploys the scripts via commands from the mobile application. To reduce the overall cost of the motor controller, we plan to create a more robust circuit which reduces the overall power loss of the voltage regulation circuits for the motor control.
The resources required to meet these new challenges would be time, which would be an entire semester or about 15 weeks, budget, which would be a very minimal amount because we have most of the equipment on hand. And since we require no additional equipment, because all we're doing is minimizing circuit components and making dimensions smaller, so our budget would be cheaper. And in terms of feasibility, we think it is a low-risk implementation because it only requires exploration of new software and circuit design techniques.
The performance gain includes a more efficient device which consumes less power and dissipates less power through voltage regulation. We'd be able to measure this by using standard data collection techniques to analyze the overall power consumption compared to the original device. The next idea would be the reduction of components or implementation of a more robust circuit, which would reduce the overall cost of the universal motor controller. We'd be able to measure this by comparing the overall cost before and after the change. A final idea would be the integration of a more user-friendly app, which would be able to improve the ability to implement more diverse sequences. We'd be able to measure this by having a new user try both applications and then give us feedback about it.
On behalf of the Royal Engineers, we'd like to thank you and we hope you enjoyed our presentation.
On our next slide, we'd like to thank and acknowledge our sponsors.
Firstly, we'd like to thank Cornell Cup, powered by Intel. Next, we would like to thank the University of Scranton, especially the Office of the Provost / Senior Academic Vice President, College of the Arts and Sciences, Dean's Office, Office of Research, Sponsored Programs, and the Department of Physics and Electrical Engineering. Next, we'd like to thank our sponsor, Backyard Ale House, and finally, Osh Park.